Okay, let's start. First of all, thank you all for joining our meeting. I frankly think that the CUDA community requires more discussions because there are a lot of subtle corners in CUDA that affect both performance and safety. And today I'll try to bring some light into one of these corners, and I'd like you to do the same. So feel free to suggest yourself as a speaker in our Discord channel if you have anything to share. Before we start, I'd like to discuss a few organizational questions. I'll be recording this presentation. If you have questions, I'll answer them after each section. Also, I'd like to point out that you don't have to have your video on or talk if you don't want to. I'll read questions from the chat, so you can ask anything there. I'm going to turn off the recording after the presentation ends, so feel free to discuss any CUDA-related questions afterward. Besides, our meeting will last as long as we have subjects to discuss, so don't hurry to disconnect. After this short message, I'm ready to start my presentation. And today I'm going to talk about the CUDA memory model. You can successfully use CUDA without considering its memory model, as long as each thread accesses the memory assigned to it. But if different threads access the same memory and at least one of them writes to it, you'll need to immerse yourself into the CUDA memory model. In other words, a memory model is all about guarantees you have while accessing shared memory from multiple threads. There are two main reasons for understanding memory models. First of which is performance. A significant slowdown can be caused by excess memory ordering. If you use memory model guarantees correctly, you can get a significant performance improvement. During this talk, I'll show an example of over 40% runtime improvement thanks to the memory model understanding. The second motivation for this subject is correctness. It is stated that one source of non-deterministic concurrency bugs is a misunderstanding of the memory consistency model. If you don't understand the guarantees given by the memory model, you are risking to produce a bug, which might not show itself for 1,000 executions. I'll discuss an example of data race that happens only a few times over 100,000 executions. I've tried to make my talk rather pragmatic, so you can get a common sense of performance benefits along with safety issues. However, I have to mention some definitions that we'll need later. And let's start simple. The read operation is a load instruction and atom instruction. A write operation is a store instruction and atom instruction. So a memory operation is a read or write. And finally, a memory model is a set of rules defining how memory operations on shared memory from multiple threads are processed. By the way, I use shared memory in a general meaning. In other words, shared memory is a memory that can be accessed by different threads. So don't confuse it with CUDA's Scratchpad memory that is also called shared. Anyway, different memory models provide different guarantees to a developer. These guarantees, in their turn, can prevent hardware from some optimizations. So it's possible to have a piece of hardware that implements quite an intuitive memory model, but it is restricted by this model to perform poorly. Regarding intuitive models, the absolute winner is the sequential consistency memory model. I consider it here so as to expose the CUDA memory model through its differences with something intuitive. Anyway, sequential consistency guarantees that memory operations can be reordered with respect to program order. Let's consider this simple multi-threaded program. So variables x and y are initialized to 0 beforehand. The first thread writes 1 to x and then reads y. The second thread writes 1 to y and then reads x. For the first thread, sequential consistency guarantees that the write to x happens before the read of y in all possible executions of this program. Here is the illustration of these executions. Sequential consistency can be formalized with the equation above. This equation states that for memory operation A that is placed before operation B in the thread's program order, it is guaranteed that A is placed before B in memory order. In fact, with sequential consistency, it's impossible for both R1 and R2 to be 0. If you haven't immersed yourself into memory models yet, you might think that it's the only possible way for hardware to behave. In this case, I have a different memory model for you, and it's one step closer to the CUDA memory model. TSO memory model allows some non-sequential consistency executions by holding stores in write buffers. In fact, most modern CPUs implement this memory model because store to buffer hide memory latency, which affects performance. So in our previous example, the reads of Y and X in second lines can start immediately after putting writes into buffer in the first lines. But how does this hardware optimization affect sequential consistency? As you can see from the illustration on the slide, now it's possible to have both R1 and R2 to be equal to 0. In other words, store buffers violate sequential consistency in one particular case, load after store. Store after store can't be reordered because store buffers are required to be FIFO. Any memory operation after load can't be reordered because it's wait till load completion. The memory model that allows loads placed after stores in program order to be reordered in memory order is called total store order. But what is program order anyway? Let's examine this particular example. I assign the sum of y and 1 to x, and then store 0 to y. If you compile this code with flags on the slide, you'll get assembly from the right. So what is going on in this assembly? Y is stored into the AX register in the first line. Then Y is set to 0 in the second line. But it's not what I've written. In the C++ code on the left, Y is set to 0 after writing to X. Obviously, an order of expressions in C++ is not a program order. The final assembly is. Fortunately, we can force the compiler to produce an assembly that matches our intents. An assembly in line 2 is called compiler barrier, and it helps to think about higher-level language in terms of program order. To understand how often load after store reordering happens, I wrote this code. As you can see, I prevented compile time reorderings with compiler barriers. The test runs this program 100,000 times and counts the number of load after store violations. And here is the histogram of results, gathered over 100,000 executions of the test. The minimal violations count was about 2% of iterations, the maximal about 99%. And I hope this histogram convinced you that hardware reordering is not a rare event. There is a way to forbid load after store reordering by placing a memory fence. So it's kind of compiler barrier that we've seen before, but it operates at hardware level. With the hardware barrier, there was no load after store reordering at all. So it's important to understand that the hardware barrier also acts as a software barrier, but not vice versa. Anyway, at this point, we've become acquainted with software and hardware CPU barriers, program order, and operations reordering. With the mentioned concepts, we are finally ready to talk about GPUs. But before that, I'd like to answer your questions about the discussed material. Are there any questions yet? Okay. Yeah.
Sorry, one question here. So to ensure this correctness that you are saying about the reordering and make sure that this reordering doesn't happen by the memory fence, how much performance overhead are we expecting here?
Yeah, so I've measured the performance overhead for CUDA because I was targeting CUDA at first place, so I haven't measured it here. But I'll publish the source code so you could measure it yourself.
I see. Thank you.
Okay, so I don't see any questions in the chat, so we'll continue. GPUs utilize a variety of hardware optimizations to increase bandwidth. These optimizations come at cost of memory ordering. If a memory model guarantees only ordering around a fence, it is called weak. And as you might have guessed from the subtitle of this talk, CUDA provides a weak memory model. On the slide, you can see a formal expression of what I've just said. If memory operation is placed before a fence in program order, then it will be before the fence in memory order. If a fence is placed before memory operation in program order, then it will be before this operation in memory order. No other ordering is guaranteed. To expose memory model weakness, let's consider this example. A writer stores values to 4 variables. Other threads load these variables and check for load order violations. I'm searching for the case where stores to first and third variables are observed, but stores to second and fourth aren't. As you remember, this kind of reordering was impossible in TSO because the store buffer is FIFO. Do you think it's possible to observe a reordering of this kind? If yes, why it happens? I mean, is it because CUDA was meant to be confusing? I suggest you think about optimization opportunities that can be taken if the reordering is allowed. And while you have this background idea, I'll show you the result. Yes, reordering of this kind happens a lot. More than 60% of iterations observed reordering on my RTX 3090. And it's about time we return to the question why. If you don't have any thoughts, I'll give you a clue. If the first 2 variables are placed in one memory segment, there is no ordering observed. But if the first and third variables are placed in one segment, the reordering happens almost every time. In order to understand this behavior, we need to look at FIFO write buffer closer. Before the write issues any instructions, there is no entry in the write buffer. And after issuing the last instruction, the write buffer looks like that. In other words, the FIFO write buffer writes will occur in threads order. On the other hand, each entry in the merging write buffer corresponds to a cache block. Writing to the first variable fills part of the first entry in the merging write buffer. The second write will fill the second entry, just like before. And here is something interesting. The third write will fill part of the first entry. The first entry of the write buffer will be written before the second one. That means that the second and fourth variables will be written after the first and third ones, just like we've seen with the litmus test before. We can fix this ordering issue with hardware memory fences. In CUDA, a memory fence can be placed by calling the thread fence function. Okay, so what's about performance? The version with fences slows down our simple test by 8%. Anyway, if you think that this reordering isn't exciting enough, I think that the next one will be of a greater interest to you. So let's focus on the else branch for a while. There are 2 reads from the Scratchpad memory. I use reordering arrays filled with zeros so as to prevent compiler optimizations. Effectively, I read the same address twice. The first thread writes 1 to Scratchpad memory. So here is the illustration of what I'm looking for. The question is it possible for these reads to reorder like that? Well, this reordering happens quite a few times on my Fermi GPU. This behavior is considered to be a bug and was fixed in Maxwell. But the origin of this issue is quite interesting anyway. To optimize band conflicts, hardware splits the sets of non-conflicting addresses into groups. This optimization makes it possible for 2 loads of one thread to be reordered if the first load encounters a conflict coming from another thread. In other words, memory ordering issues are a function of workload. It was quite difficult to reproduce this behavior. Until I introduced randomized memory accesses performed by different threads, I hadn't observed ordering issues at all. So, are there any questions about this section?
Can you please go back one on the previous slide? I just want to look at it again.
Yeah, this one.
No, previous.
Yeah.
Yes, this one.
So reordering 1 and reordering 2 is virtually the same array. So it's just a way to force compiler to read the address twice.
Okay, got it.
Okay. Let's consider another example. One thread fills data and sets the flag to 1 afterward. Other thread spins on the flag and then reads data. This pattern is quite common. It is called message passing. Write-to-code assembly looks fine. It stores 1 to the flag and after writes to data. And readers assembly is more interesting though. It loads the flag, then jumps to the L1 label and spins there forever, unless the flag is true. Obviously, this program never ends in most executions, but why could a compiler did this? That's because the L1 cache isn't coherent. Moreover, each SM has its own L1 cache. That means that if the value gets there, it won't be changed, no matter how many times you read it. So the compiler optimizes this code by removing the reads of the flag. This optimization doesn't change the behavior of the program anyway. And we can partially fix this by using the volatile keyword on the flag. Volatile forces the compiler to load the variable each time it is referenced. It also forbids hardware to put the value into the L1 cache. In other words, the volatile keyword ensures that the writes will get visible by other threads. Anyway, with the volatile keyword, assembly looks better. It loads the flag in the second line, checks its value in the third, and jumps to the L1 label if it is equal to 0. Just what I wanted. The generated assembly represents our intentions. And it's about time we remembered about hardware reorderings. Here you can see a histogram of message passing violations. In other words, it means that the previous code read stalled data. It is interesting that for different data size, I got different results. For thousands of iterations, I haven't seen any reordering for the input size of 1 and 8. It doesn't mean that you can omit fences in this case. As I've shown before, memory reordering is a function of both memory allocations and workload. So let's fix this test. By placing memory fences after writes to data, we ensure that these memory operations are observable by different threads. After that, we can safely set the flag to 1. I also should add a fence to readers. Without a fence, there are no guarantees that the data isn't cached in L1. Okay, does it mean that your only option is to use the thread fence with every possible memory ordering issue? Fortunately, there are other options. For example, we can force readers to bypass L1. With inline assembly on the top of the slide, it's possible to load directly from a coherent L2 cache. As you can see, the writer's code isn't changed. I've removed the fence and replaced direct loads to load that bypasses the L1 cache. And this version is faster. The average speedup is about 8% if the maximal size is 1 int. I've called this version without fence controversial because there are no official guarantees regarding loads order. I haven't managed to find anything about this subject, so I decided to ask Olivier Giroux, who is an architect at NVIDIA, about the safety of such optimization. With his permission, I quote his answer here. He said, "It's possible to break the dependency order between the flag load and the later dependent CG load that makes your test pass. Because it's possible to write a program that breaks this order, it's not possible for us to write a memory model that says that the order is enforced." And besides the possibility to break the ordering, if you pass bigger messages, you'll get a significant slowdown. But why? So the reason for this slowdown is the L1 cache. Optimized version omits fence after spin loop at cost of direct L2 loads. On the other hand, the version with fence flashes L1 right after the spin loop, but after the first load of data, the code enjoys reading from L1, which is faster. To sum up, direct L2 loads can be used for small message passing optimization, but there is a way to break code. I'm going to show you both faster and safer way for the case of small message passing. The fence can be eliminated if the status flag and the data can be combined into a single architectural word. That is, instead of enforcing memory ordering, we could produce a single memory operation for both data and flag. Here I introduce a union for the flag and data that are stored as a single int64 value. As you can see, I write data to global memory by assigning the int64 variable. If you are bound to use 64-bit data, you can use 128 byte words instead. And this approach gives us another 30% speed up. Well, that means that you don't have to be like that guy with a flag state. The plot that you are looking at could be considered quite synthetic. So let's put this knowledge into practice. But before that, it's better to be on the same page. If there are any questions, I'm ready to answer them here.
I would have a question about that memory passing example.
Yeah.
Could that also be fixed by making also data volatile?
No, because as you can see from the previous example, all of the variables were marked as volatile, and still the reordering happens. So only ordering around fence is guaranteed.
I see. Yeah, thank
So
you.
here the fence fixed the issue. Okay, so no questions in the chat. So let's continue. To test everything I said on a real-world code, I'm gonna optimize the scan algorithm. Scan produces an output sequence where each element is computed to be the reduction of the elements occurring earlier in the input sequence. You can see a serial implementation of scan on the slide. There is a variety of algorithms that implements thread block scan on GPU. What I'm interested in is GPU-wide scan implementation. So let's consider the example on the slide. There are 3 thread blocks. Each block is assigned to process 2 elements from the input array. We can write a result of partial scans of each block into the output array. To produce a final result, we need to somehow combine these partial results. Let's compute a reduction within each block and write the result into a separate array. After that, we can compute an inclusive scan on this array. And now we can take the result of the inclusive scan of the previous block. This value represents the sum that we need to add to our partial result to produce the final output array. In code, it could look like this. The first kernel computes a partial scan array and writes per block with sums into helper buffer. Then I compute the prefix sum of the helper buffer and finally adjust values in output arrays. Putting the code into separate kernels provides us with some guarantees about memory ordering. In other words, if the second kernel starts, all the thread blocks will have written their partial results into the helper buffer. As you can see, this approach lacks performance. This is due to the fact that the code needs to read and write the data twice. The code reads input data and writes partial results on the same size. Then it reads partial results, adjusts values, and writes it back. In some books, you can find the solution to the issue with extra memory traffic. The solution is to wait for the previous thread block to write the sum into memory, and then adjust blocks values within one kernel launch. Let's start implementing this approach. It loads thread data size values into each thread's registers, then performs reduction within a thread block. Here comes the interesting part. The first block writes the result immediately. Other blocks spin on the flag of the previous block. Then the result of the previous block is observable. The result of the current block is added to the partial sum. The result is written to the global memory in order to release subsequent blocks from spinning. Then the code performs the final scan and writes the result into global memory. And this code performs even worse than the one with 3 kernels. We can actually remove any operation except message passing to find out that the time is almost equal to the message passing itself. But the books told us that it was better. Maybe something wrong with my 3090. So here you can see how different GPUs perform this message passing benchmark. Clearly, there is nothing wrong with my 3090. The problem is in the serialization of thread blocks. The latency of message passing between blocks is too big to optimize the scan like that. Fortunately, NVIDIA came up with a solution. Instead of waiting for the previous block, let's gather partial results of previous blocks until we find the final result. I'll describe this approach in detail. Now the flag can take 2 states. If the flag is in the first state, it means that the block has computed the final result. If the flag is in the second state, it means that the block has computed only partial results. The first thread block writes the final result immediately after computing it. Other blocks write only partial results immediately. Then the first warp of each block searches for the final result as following. Each thread of the first warp spins on the previous block assigned to it. Effectively, we need to wait until the last, at least partial results of the previous blocks are observable. If only the partial sums of 32 previous blocks are written, we continue going deeper into the result of thread blocks with smaller indices. If one of the previous blocks is in its final state, the thread of warp vote to find the closest block with their final result. Then the warp computes warp reduce to find the final sum of previous block's results. And just like before, the code adjusts the results of threads and writes it to memory. And now we get the improvement over the version with 3 kernels. The code performs on the speed of memory copying. That means that it can be further improved. I've recorded how many cycles each block spent in the spin loop in the naive single kernel version. You can see that each block executes more than 1,000 iterations before getting the result of the previous block. On the other hand, with decoupled lookback, the first warp of each thread spins a few iterations and then goes deeper into block states array. On average, each warp goes deeper into the array only 4 times. That means that a warp examines 128 blocks on average. Okay, let's return to my previous question about the performance of a single word approach. Using fences instead of single word approach showed performance degradation of around 23% on performing a scan. So the single word approach performs better in real world programs as well. Any questions regarding single kernel scan?
Yeah, hi. I had a query on regarding the synchronization of multiple threads here. So, will that be possible?
I didn't quite get the question,
Uh,
sorry. So
the synchronization of multi-thread blocks.
So this scan is about GPU-wide scan. So it is a multi-block execution.
Oh, okay.
So
Yeah.
as I mentioned, the inter-block scan is not of big interest because it's kind of simple. The interesting part comes when you need to combine results of different thread blocks And here the memory model play a big part. So what I wanted to show here is that using a single architectural word, just like here, improve our performance about like 23% over the version with fans, because normally you'll need write data, perform thread fans, and then write some flag. And here I combined flag and data, so I don't need thread fans at all. And the synchronization itself is performed by spinning on these variables here. So effectively, we wait for this memory to change, to be changed, without thread fences.
So this is here zero copy is involved. The memory with respect to the memory,
So
or the memory modules though are copied to the other blocks too.
So this is these flags are stored in global memory.
Okay.
So yeah.
Thank you.
So there is a question: is it possible to get full code of single kernel scan? Yeah. So I'll publish all the source codes soon, but until then, you are able to look at kube implementation.
Okay, yeah, thanks.
Because it's effectively, there is a article about decoupled loopback. It's what I used to write one. And the kube is published at GitHub, so yeah. Okay, so let's continue. If you open documentation for the PTX memory consistency model, you'll find a description of release acquire patterns. And the first pattern is quite similar to the first version of message passing implementation that we've discussed. The release pattern consists of a memory fence followed by a strong write. Acquire pattern consists of a strong read followed by a memory fence. Anyway, what is a strong operation? And it's about time we return to the definitions. A strong operation is a memory operation with a relaxed acquire, release, or volatile qualifier. These qualifiers exist in the PTX assembly. For example, if you mark some variable as volatile, memory operations on it will be compiled into a load or a store with a volatile qualifier. But what about other qualifiers? Unlike volatile, you can't use them directly from CUDA. You'll need to use an inline assembly for that. I've written wrappers for the release and acquire qualifiers. The second release acquire pattern from the documentation relies on them. The documentation states that you can get a release acquire pattern by using the release operation on the writer's side and the acquire operation on the reader's side. And you might be wondering, how is it possible to have a memory ordering without a memory fence? So in reality, there is no magical instructions qualifiers. Because if you compile a write with a release qualifier, you'll simply get a memory barrier and a strong write, just like we did with thread fence and volatile variable. And on the reader's side, the acquire qualifier will be compiled into a strong read followed by a cache invalidation instruction. New libq++ library relies on these instructions, but provides a better semantic. We could change the flag type to libq++ atomic and forget about memory fences and volatile keyword. As you can see in line 6 of the bottom listing, we can clearly express ourselves by calling the store method with memory order release. To show more examples of this library, I'm gonna discuss another optimization opportunity. And this time, I'll write a single kernel reduction. Reduce produces a single aggregate from a list of input arrays. Well, just like before, I'll focus on calculating the sum of the array. Because we have one result value, we'll face the same problem of combining partial results of thread blocks. One of the solutions is to use atomic operations between thread blocks, but it is not always possible. For example, if you are bound to have run-to-run determinism, you'll need to store per block values and reduce them later. The common approach is to write intermediate results into a helper buffer and execute a single block to reduce it afterward. We could remove the second kernel call by asking the last block to reduce the helper buffer. I don't expect this optimization to change the performance a lot, but it will be possible to show a few more useful concepts here. The only difference with the two-kernel approach is at the end of the kernel. The first thread of each thread block writes its partial result, performs thread fence, and increments counter. If the current thread block is last, it performs a final reduction. It's important to note that atomic operations don't imply memory ordering. That's why we still need a fence here. I've seen quite a lot of implementations that use atomic operations with release semantics and yet omit memory fences. Clearly, it leads to concurrency bugs. Also, an atomic operation is classified as a strong one, so you don't need to mark the counter as volatile. I got an average speedup of single kernel approach around 4%. So let's try to use libq++ instead of atomic intrinsics. With atomics provided by libq++, we can modify the code as follows. Now it's difficult to forget about thread fence because it's embedded in the fetchhead method. And something gone wrong here. The new implementation is 3 times slower, 2 kernels one. Actually, libq++ has different atomics. The one that is in CUDA atomic header allows an extra template parameter. It can be used to reduce the scope of the atomic operations. And what I needed was atomic with GPU scope. After changing the type of atomic, the performance matches the handwritten code, so be careful. And to demonstrate a few more libq++ features, let's consider the last problem. We have a two-dimensional grid. One of the grid cells contains a sensor. We need to perform some computations until the sensor is triggered. And I don't want to download data from GPU to decide upon the continuation of iterations. And to eliminate extra latency, let's organize the code as a persistent kernel. In order to stop all threads, we need to pass some information from one thread to all others. Effectively, it's a broadcast problem. To have a reference, let's pretend that the sensor is located in each cell and it is triggered simultaneously. The code performs some computations on line 9, and if the result is greater than the threshold, the iterations are stopped. To leave only one sensor, we need to modify the code as follows. The sensor owner checks its results and stores the flag along with current iteration number. Reader threads load the data and spins until their iteration number is not equal to the writer's one. Because of the enormous contention on the flag, the elapsed time is significantly distributed. That's why I use probability density plots to analyze performance. As you can see from the plot, the difference between the two versions is significant. Before optimization, let's introduce a hypothesis. So I presume that the source of poor performance is in high contention. So we can reduce contention by allowing only the main thread of each thread block to spin on the flag. When a new value of the flag is observed, it's broadcasted to the rest of the thread block through Scratchpad memory. Let's pretend that we have only 2 thread blocks. Then the mentioned grid can be divided between them as follows. In this case, the communication pattern is presented on the slide. As you can see, the number of memory accesses is reduced by a factor equal to the size of a thread block. The performance of the new version is much closer to our reference. I suppose that our premise was correct. The performance is limited only by the flag contention. If that is the case, can we reduce contention even further? Fortunately, we can. Since Volta, there is an intrinsic that suspends the thread for a while. The intrinsic usage is illustrated in line 6. An argument of this nanosleep is a sleep duration in nanoseconds. And here are the performance results. Although the improvement was quite naive, we got a significant difference in performance. As you know, there are general practices for spin loop optimizations. For example, we can spin without nanosleep for a limited number of iterations. This might reduce latency at cost of increased contention. Or we can change the sleep duration during the spin loop. Fortunately, libq++ provides an implementation of an atomic weight for us, so we don't have to write one. Here I show a change in the code of the sensor owner. I've changed the type of the flag. It's libq++ atomic with a device scope now. The sensor owner uses the store method with a relaxed memory order. Readers use the wait method in the line 6. It spins until the value is equal to the first argument. For some reason, it returns void, so we have to implicitly load a new value afterward in line 7. Unfortunately, our handwritten version of the wait was more efficient. At first, I thought that the reason is in the extra load after the wait method call. I've changed the wait implementation so as to return the last loaded value. But the modification was insignificant. So besides that, I removed a part of the fast reads from the wait method. And as you can see, it was a source of the slowdown. It seems that it's unrealistic to have both optimal and general spin loop implementation. I've shown this example to demonstrate that the pattern of memory accesses should significantly affect your decisions. In this particular example, any latency optimization on the spin loop increased contention and reduced performance. So the main rule of performance optimization holds: always measure. Are there any questions so far?
Hi, I had a
Hello.
query with respect to the size of the atomic blocks or the threads. Is there some performance considerations with respect to the memory that needs to be allocated? Yeah, some optimal considerations. So I was.
So I just used something like int64 here. Just like before, I use single word approach. Where is it? So here you can see that flag is int64, and I use some structure with union just as I've shown. So I haven't measured this effect of underlying type on performance. So maybe you'll do it and tell us something later when you get the source codes.
Cool.
Okay. So if you read my latest blog post, you know that I can't help mentioning the multi-GPU systems. Fortunately, there are not many differences from the memory model point of view. The common scheme of multi-GPU systems is shown on the slide. All mentioned concepts are valid for multi-GPU systems thanks to the fact that the requests to the different GPU go through its coherent L2 cache. That means that our broadcast example works just fine on multi-GPU systems as well. I've allocated the flag on the second GPU. When the main thread of the first GPU's thread block accesses the flag, it reads remote L2 cache. To observe some speedup of multi-GPU execution, I've increased the grid size. The mentioned code parallel efficiency is close to 100%. The only difference is a smaller speedup of the version with sleep. Clearly, the second GPU introduces higher contention. Therefore, a more adaptive approach to the selection of sleep duration is needed. There are more interesting details, so if you are interested in this subject, check the materials on the slide. I'm going to publish the presentation and the source code soon, so you can get the link from my Twitter or Discord channel. And I'd like to conclude this talk with a call for you to try and use concurrent algorithms for post-Volta GPUs. It's clear that huge efforts were put into both hardware and software design so as to let us rely on memory model.